Hello guys, welcome to my YouTube channel. And in this video, we are going to see about what is simple linear regression. This video is going to be a simple one. A lot more of mathematical equations aren't be up this video. So just free up your mind and just focus on what I am saying in this video. The mathematical ones are coming in my upcoming videos. Okay. So what is a simple linear regression? So this is a supervised problem. Supervised in the sense, in my previous video, I have mentioned that supervised is nothing but we will be having a dependent and an independent features. Like the same wise, simple linear regression just models a mathematical equation of that is when I feed an input of x, I would get an output of y. So simply, this is what we are going to achieve in the simple linear regression. But the transformation of x such that which is the independent feature into a dependent feature of y is dependent on some sort of mathematical model. That is, x moves into some sort of mathematical model and then it produces a output of y. So this mathematical model can be modeled as y is equal to m into x plus c. So you can see here that our independent feature of x is the input and y is the dependent feature which comes out as output. So basically what we're trying to do is we would feed the input x and our output y is given. Okay. We can also mention it as y hat, which is the predicted one. Okay. So what are these two m and c denotes? So these two m and c are a crucial part of the simple linear regression to predict the input x to output y. So let's get the intuition of m and c. Consider consider a simple coordinate system of x and y, and here we have some sort of some lines. Say for example, this is my line, okay, and this is my feature one. Say for example, it's my weight, and for this weight, I am getting the corresponding output as height. Okay, so this is my weight and my output height. So this is a simple linear regression, and you can just specify the slope and see as slope change of slantness in the line. So you can see here, so this particular shaded portion is actually the slope. And what about the intercept? The intercept is actually this particular linear regression line intercepting at the y-axis. Okay. So I think you got clear about what is the equation of y is equal to m into x plus c. Okay. So now, what we are just trying to achieve here using this simple linear regression. What to achieve? So we have to just fine tune or just make these m and c values so accurate or else somewhat accurate such that whatever future values are fed into this x as input, we get a decent or somewhat accurate output as y. So this is what we have to achieve in this particular problem, that is a simple linear regression. So how we can achieve it? So by utilizing gradient descent technique, we can fine tune the values of m and c so that we get an output of y from the input x. Okay, so let me explain you. I think this is the overview of what we are just trying to achieve in this video. Consider the simple data set of x, y, and I'm having three inputs, 1, 2, 3, and the output for this is 2, 4, 6. So consider this data set as it was given to me by a client named XYZ is the client. So they have given me a data set containing three rows. And what the problem statement which I have received is, so using this data set, I have to make a mathematical model such that whatever future data is given by these client companies, I have to predict the suitable output. So this is the problem statement which was given to me. So how I am going to achieve it? So first example, this is a simple linear regression. So I'm going to utilize the equation y is equal to m into x plus c. Okay. So initially, I will be fixing the values of m and c to some arbitrary values. So in my case here, I am fixing the value as m is equal to 1, and let's just keep it simple by keeping c as 0. Okay. So for m is equal to 1, my output y, for m is equal to 1, let's just calculate what's the actual output, what's the predicted output. Okay. So m is equal to 1, and in this case, x is 1. So 1 into 1 gives me 1, and 2 into 1 gives me 2, and 3 into 1 gives me 3. Okay. So by keeping the slope, that is m as 1, I am getting the predicted output as 1, 2, 3. Let's just fit this data in a coordinate system. 1, 2, 3. So for x1, I am getting the output as 1, 1. So for x2, I am getting the output as 2. So for x3, I am getting the output as 3. Okay. So for this condition, my intercept c is 0. So which says that my linear regression line is directly passing into the origin. So this is the line, but this is the actual points, right? So this data set is given by the client company. So I have to utilize these data points. So 246 is the actual output. So where those two occurs. So for the 1 comma 2, 1, the output is 2, and for x is equal to 2, the output is 4, and for x equal to 3, the output is 6. Okay. So this is my actual output, but I have made a linear regression line which fits for the output as 1, 2, and 3. So now there is a huge error between the actual and the predicted ones. The error can be calculated as error function is defined as the difference in the actual and the predicted for each dataset. So for here, the dataset has an error of 2 minus 1, 1, 4 minus 2, it is 2, and 6 minus 3 gives me 3. So 1, 2, 3 are the errors. Okay. When I just sum up all these to get the huge error, which is called as the cost function. So the cost function can be named as j of, for this particular m and c, summing up all the errors. For this, I have been using the mean square error. Mean square error is nothing but summing up all the squares of the errors. Okay, 1 by 2 into the total number of the records, summation I is equal to 1 till n yi cap minus yi the whole square. Okay, so let's just evaluate this. So I have totally three records. So 1 by 2 into 3, and the summation of these three records, which is yi cap minus yi. So our predicted y is 1, and our actual y is 2, right? 1 minus 2 the whole square plus, and then this 2 minus 4 the whole square plus 3 minus 6 the whole square. So this would just give me some output. Let's say, for example, uh, after calculation, it gives me 4.6 as the output. Okay. Okay. I think you are all clear up to this. So let me just brush up what I have just given. So I have considered the slope as m is equal to 1, c as 0. So for m is equal to 1 and c is equal to 0, I have got error, that is the cost function of 4.6. So which says that also this is the line, this is the actual data points, and this is the best line right now till I have placed. But you can see here that the best fit line till now and the actual data points has a huge difference. So we have to minimize this difference. So as I actually said in the previous um, few minutes ago, which is in the what to achieve statement, we have to utilize the gradient descent such that the M and C are optimized such that it produces the best values of Y when the input is given as X. Okay. So for this, we will be utilizing the gradient descent. So what does gradient descent does? So for the slope value of 1 and C value of 0, we are getting the cost function as 4.6. So let me just plot this in the graph. So my x-axis has a slope and the cost function is the y-axis. So for the slope 1, I am getting the cost function as 4.6. So say for example, for the slope value of 2, I am getting the cost function as 2. And for the slope value 3, I am getting the 0 as the cost function, which is no error in the data set. That is, when for the slope value of 3 and the C value of 0 gives me no error in the mathematical model which I have defined. So when I just connect all these dots, when I connect all these dots, so you can see here, I'm getting some sort of equations where at the global minima, I'm getting no errors. So now I think you should have just guessed what I would be just saying. So we have to try out with several slope values. So m is equal to 1, m is equal to 2, m is equal to 3, such that for which m value my cost function is minimal, is global minimal. So this particular problem statement is a tedious one. So we have to just try out with several sorts of slope values. Uh, the list is so much exhaustive, such that the manual work wouldn't be an efficient work. So we have to bring up with some sort of techniques or mechanisms such that we would be automating this particular work of finding the suitable slope values to minimize the cost function. So what can be the suitable mechanism? It's obviously, as I previously said, it's the gradient descent. So in my next video, I will be explaining the gradient descent and how to utilize this gradient descent to fine tune or optimize the M and C to minimize the cost function. Okay, so let me brush up the concepts which I have delivered to you. So given an independent feature of X and an output of Y, and this is my actual data points. Okay, so and then I have to just fit a line such that the errors between the actual points and the line is so minimal such that whatever input is given in the future X as X, the output from the produced Y is always minimal, and also it should be accurate. So this is what we are achieving in the simple linear regression. Hope you understand this. Let me catch you up in my next video. Thank you.